Well, hello SINUMERIK Nation, and welcome to another episode of Simply SINUMERIK Live. I'm your host, Chris Pollock, and today we're going to look at thread milling. So why thread milling? Why would I want to thread mill over my traditional tapping type of scenario for cutting threads? You know, we've all been tapping probably the majority of our machinist career. So what would be the benefits? I mean, on the outside looking in, looks like it might be a little bit more cumbersome than, the traditional tapping scenario. Well, one of the first things that really comes to mind when I think about thread milling is really control. So one of the challenges with a tap, and I think all of us know it whenever we've especially had to do like a bottoming type of application, is the lead to the tap. So I have some decent tip projection that I always have to compensate for, and then I have my lead where I have non-effective threads. On a tap, obviously I need that for engaging the tool, starting the cutting process. In a thread mill, I don't have to worry about all that stuff. So I can literally thread right to the bottom of my hole if I want, and I really effectively don't lose much geometry at all in that type of scenario. Now, additionally, not only does it give me more control, but God forbid I break a tap, right? We've all been there, we've all done it. It's never a fun thing to do. I've scrapped the part. I spend maybe hours trying to extract that tap out of the hole so I can salvage the part. So with a thread mill, I can control how much chip load I'm putting on my part. I can ease into the geometry a little bit more. It's not a one and done type of scenario that I have with a tap. So for sure, and God forbid the thread mill breaks, it's not jammed into the hole like a tap is. It's smaller than the hole, so you can certainly fish it out and potentially salvage your part a lot more. The other thing, chip control, certainly that can be a factor, especially when tapping, right? I got to really pay close attention to my tip geometry. Is my chip being pushed forward? Is it being pulled back? If it's being pushed forward like a standard hand tap like this, I'm going to get binding. That's more I have to accommodate at the bottom of that hole before I send the tap in. I get a lot better chip control with a thread mill. And speed. And speed's a big factor. You may look at it and think, well, how could thread milling be faster than tapping? But in fact, if I use the appropriate tool, I could potentially thread mill in one helical shot. So one quick helix, which is the motion of really the pitch of my thread, right? The distance from crest to crest or root to root, and I could get the entire thread machine. So hopefully after today, you'll see that it is a significantly faster application when leveraged properly with the right tools. Now, tools is the point, the next step in deciding how we thread mill. And really that comes into, there are a lot of different tools on the market for thread milling. So when I started going down this path, and I knew I wanted to produce this video because I get a lot of questions on thread milling, I started looking at the YouTube content that was out there. And for sure, there are a lot of great videos on YouTube about thread milling. But I would say certainly the bulk of the videos are around a single point thread mill or a single tooth thread mill. So what that means is that thread mill, one helix, would only generate one thread profile or one pitch of that thread. Now that is a great tool to have sitting in the toolbox. God forbid I get into a bind, I have to cut a thread geometry, I don't have that tap, or I don't have the appropriate thread mill, I can get through it. However, it is a very slow process. The tools themselves you can't push very hard on, so you have a tendency to do quite a few passes with them. I have to helically interpolate the entire thread, no different than a tap. So if anything, those tend to be certainly slower than a traditional tap. But we're not going to use that. What we're going to use is a multi-tooth thread mill. So this, you look at it from the surface, almost think, boy, that looks like a tap. Looks very similar to a tap. But what it's going to do is it's now going to allow me to cut the entire profile in one helical path. So what am I using for that? Well, what I did was I took a look at the different manufacturers, and I found that OSG had a really interesting tool on their AT-1 series thread mills. And why is it so interesting? Well, it kind of took a new approach to the traditional thread mill. And one of the key features to this tool, as opposed to a traditional multi-tooth thread mill, is that it is a left-hand helix, but a right-hand cut. So what do I mean by that? Well, I mean you're still going to spin the spindle clockwise to cut the thread profile, but the helix that is cut or ground into the tap is reverse. So what does that do? Well, instead of the nature of the machining process, my tool wanting to push away from the material, that left-hand helix kind of wants to pull the tool into the part. Even in a climb milling scenario, it's going to want to suck that tool in. So effectively, it's going to transfer the load during cutting as close to the spindle as it can. Right? That's a key factor, because the further away from my spindle bearings I get, the less rigidity and the more deflection I'm going to see. So by having this left-hand helix, it pulls the load into the spindle, and it's going to really allow me to potentially cut one pass and machine that thread right to size. I know when I first was told, I was skeptical. I've done it, we'll see it. You can certainly cut one shot. Now, depending obviously on materials, I think more likely than not machine rigidity, you may need to introduce a second pass in certain scenarios. But effectively, you can take this tool and cut one pass and machine the entire thread geometry. Now, a couple other things that they've done that's unique about this tool. It has a variable helix. So the helix obviously is that spiral going up the shank of the tool, right? The geometry of that tool. Well, that helix is changing. And by changing that helix, you change the harmonic of the cut, so it allows the tool to be a lot more stable when machining. Additionally, they did another thing that's used quite commonly in end mills, is an unequal index. So let's say I have 3 flutes, right? I got 3 fluted tool. Normally, I would expect the index of each of those flutes to be 120 degrees, right? 360 divided by 3. Or in this case, I have a 5 fluted, so it would be 360 divided by 5. So what they do with an unequal index is they change that. So not every flute is the same angle from the last. That, just like a variable helix, gives you a lot more stability in your cut, which allows us to get to the Holy Grail, which would be taking this in one shot. Okay, so we're going to explore 2 different applications today. One, we're going to use this tool. We're going to machine a 1/2 by 20 fine straight thread. And then we're going to go back, and we're going to do that in a block of aluminum here. Then we're going to go back and we're going to put in an MPT and go into a tapered thread, because there are some different things that we have to anticipate when we get to taper threading as opposed to straight threading. So we will look at both applications. In the straight thread, we're going to do a standard nominal 1/2 by 20 2B class thread geometry. And then we are also going to do a non-standard geometry. So in this case, we're going to take the same tool, go in and effectively cut a 1" by 20 thread. So I can use this tool for all kinds of different ranges of geometry. Now, obviously, I would be limited to going any smaller than the tool is ground for, but I can certainly use it for larger non-standard profiles as well. Before we cut it though, I do want to go into some of the information we're going to need to look at when we start to program and prove out this thread mill process. So I don't want to go to that. I want to go to my 1/2 20 thread chart. So this was pulled out of all of our favorite reference material, the Machinery's Handbook. And this gave me a chance to kind of dig into the geometry or the dimensions I'm going to need to know for the thread when it's time for me to machine it. So in looking at the handbook, the reference table, some of the things that I need to know, I first need to figure out the pitch. So the pitch is critical when we go to program. I can define it in our control as threads per inch or as physical pitch, but I need to tell the control what that helix is, because that's my advance as I spiral around in my X and Y, how much am I going to move the Z. So right out of the handbook, we see that the pitch is 50 thou. Now, if you didn't have the handbook handy and you wanted to figure out quickly the pitch of any thread, in the US, on an inch threads, we happen to always define everything as threads per inch, right? How many threads will I get over a unit measurement of 1 inch? So if you just take 1 divided by that number, in my case 1 divided by 20, that's always going to give you your pitch as well. And you can see that formula right there on the bottom of the screen. Once I have the pitch, I do need to know the hole size, right? In this case, I do need to pre-drill, so I have some room to get that tool down into the hole so I can machine the thread. So the hole size, certainly you can go to any of your standard reference charts, and depending on your engagement you want, that's be how much of the effective thread is left after drilled, you can pull that out. So our standard reference charts for a half 20 is going to give us a 29/64 hole, and that's going to give us about a 75% engagement. Now, if you want to do a quick formula, maybe you don't have a reference chart handy, this is a pretty good approximation that's going to get you close to that size. So if you take the major diameter of my thread, in my case 1/2 inch, I subtract the pitch, 50 thou, that's going to get me 450, putting me right in that range of my 29/64 size. So that's just a quick formula you guys can use to figure out hole size for any tapped hole, and that'll work whether I'm tapping or I'm thread milling. The thread height, well, that's going to come right out of the machinist's handbook. Now, when I'm machining with a thread mill, really all I need to do is know a couple different things. I need to tell it what the major diameter of the thread is going to be, the largest portion of the thread, in this case because I'm going to do an ID thread. As well, I need to tell the system kind of where that wall is for the hole. And we do that by giving it the thread height. Now, the thread height has a couple different formulas or calculations you could look at. So if you start to dig into thread geometry, you'll see that there's formulas for calculating thread height as a sharp thread, or thread height with the actually predefined flats that would be there on any specific thread. Any thread you call out, there are specific thread flat sizes at the crest and the root of that thread. In thread milling, this is a non-critical dimension, so I typically would use the formula for calculating a sharp thread. It's right in my book there of 043. If I want to calculate it, it's 0.86603 times my pitch will give me the height of any thread for a sharp thread. Major diameter is going to get pulled right out of my machinist handbook. Now you do want to be careful about that. A lot of people kind of fall into the trap thinking that everything's about the major diameter of the thread, and it's not. It's your pitch diameter, which is happening at the center of the thread, is the most critical dimension of your thread. So effectively, you will find that you're probably going to go a little bit oversized to this 1/2 inch, so you can hit the pitch diameter once you start gauging your thread. Now, tool diameter is critical when I go to cut it, and this is a scenario where you're going to want to take a look at this specific tool. You could go and measure this tool off of your presetter, and I did measure mine. But what's nice about the OSG is they actually give you a dimension right on the box, and it's this RPRG value. And what that is the effective radial dimension that they want you to program to. So they already know, because they designed this tool, what size radially I'm going to want to use at the control to get me as close to hitting the dimension that I want on my thread. So the RPRG value spec'd on this tool, this 1/2 is 4.33 or 4.310 millimeters. You see that down to the lower right-hand corner of your screen. Now my machine not only is currently sitting 1 inch, but it is also sitting in diameter as far as my offset table. So I just had to take this number, convert it to inch, multiply it by 2. That gives me a tool diameter of 0.3393. Next step, certainly I need some speeds and feeds. So I can look at the manufacturer's recommendation, certainly talk to my tooling guy. When I looked at this application, they gave me a range from 1 to 2 thou per tooth as far as my feed rate, and my surface footage of 400 surface feet. At that stage, now you have to actually do a little bit more math. So this geometry right here is going to allow me to get close to programming a part, but probably one of the biggest stumbling blocks in thread milling that a lot of people don't realize they face is your feed calculation. So the feed rate I was given, I would normally go in and I would plug it into the two formulas you see at the very top of the screen, right? I'd calculate out my surface footage, so that's 3.82 times my surface footage divided by the tool diameter. That gives me a 4,500 RPM, and then I'm going to use that to calculate my feed rate. So if I plug the 4,500 RPM with my 1 thou per tooth, knowing that I have 5 flutes on this tool, that's going to give me an effective feed rate of 22.5 inches a minute. That is not the feed rate you can program for programming this thread mill geometry. And the reason being is feed rate, when given to you as a standard value, because they have no idea what size potentially thread you're cutting with this. It could be a non-standard nominal. This would apply to really just about any of their tool geometries. That is a feed on a linear path. You are not moving on a linear path, you are moving on a circular path. So that would be the feed rate I need to be doing at the cutting edge. But when I program, I'm working from the cutter center. So you have to do a calculation now to calculate what is the feed rate at the middle of my tool. Now in this case, my surface footage is all spec'd around aluminum. I'm cutting 6061, but it doesn't matter the material. I still need to go in and make this calculation. So I gave you two different formulas here at the bottom of the screen. One is for an ID thread, the other one's for an OD thread. So the way it works on an ID, to calculate the feed rate at the center of the cutter, it's going to be the feed at the cutter edge. I, in this case, know it's 22.5. That's going to get multiplied by the diameter of the part minus the tool diameter. And then that whole thing is going to get divided by the diameter of the part again. So if I start plugging these numbers in, certainly I want to subtract my 393, my tool diameter, from my part diameter. That would be the largest point at which this tool is cutting. Multiply that by my 22.5 and then divide it by the part diameter again. That's going to spit me out a feed rate of 7.2. That is the feed that I need to use when I'm machining this part. If I do not use that, I will speak from experience, it tends to not go quite well, especially in more unforgiving materials. Certainly aluminum, I could probably get away with it, but you are not running anywhere near the chip load and feeding speeds that you need to run. Okay, so we are going to now take a look. We're going to load up this part. We're going to take a look at the part program, and we're going to kind of discuss how the SINUMERIK control handles it. Certainly you could be doing this longhand or being driven from a CAD/CAM system. The other thing too is if you don't have CAN cycles built into the control like I have here, OSG has a great thread mill program generator right on their website you can get to, and it'll actually output the code for you. So certainly check that out depending on the control system you are on. For us, let's fire up our drives. Now obviously I preset an offset here, save us some time. I pre-drilled some holes so we have something to work with without wasting a ton of time. All right. Now, from a programming perspective, first I needed to build the tool, right? So if I go to my tool table right here, there we are, and I go to my 1/2-20 tool, I do need to give it a length. Now, the length was super easy. That I just let it go over to my Marpros tool setter and measure the tool length. I have my machine set up from gauge line to tooltip. That's why I have a positive value here. The diameter, that's coming from the calculated diameter on my RPRG value, right? We did the math before. We took the metric number, multiplied by 2, and then converted it. And then I do want to give it the number of flutes, especially if I'm going to let the machine do any calculations. Our control has the ability of doing some math here to calculate if I put in feed per tooth and surface footage at the control. Once I've built up the tool, then it was really just a matter of creating the part program. Now in my case, on my straight thread, I did pre-machine, a quick little pocket in my part. So we'll go back and look at that when we actually cut the non-standard geometry. I drilled a few holes. I used that 29/64 drill right there in my drill chuck. Just made sure, obviously, I gave it enough depth. Here I did a little pecking cycle to it. All pretty standard stuff. The magic comes in when I go to my thread milling cycle. So in this thread milling cycle, I'm now going to start plugging in some of the values that I just found that from obviously looking at my machinery handbook and calculating my feeds. So first, you notice I'm plugging in my 22.5, so my linear feed. Now you're going to ask, well, why didn't you just go through giving me this whole lecture about calculating feed rate? What's unique about our control is we will apply the calculation that you just saw live at the system. So I don't have to do that extra math. A lot of other controls don't do that. So if your control doesn't compensate for it, you do need to put in the new calculated value. Put in my RPM. In our control, we can also program surface footage or feed per tooth, right? I can do either one I want. But I'm plugging in the speeds and feeds that we just calculated to show you. Roughing, finishing. So if I want to take multiple cuts, I would put it to roughing. In this case, I'm going to take this thing all in one shot. So we can take a look and see how she cuts. Now, my strategy as far as cutting, do I want to start from the top and go down or start from the bottom and go up? Well, this is going to control whether I'm climb milling or conventional milling. So a lot of times when you look at somebody and they're machining an ID thread, a right-hand thread, milling it, you'll see they work from the bottom up. And they do that because that allows me to be doing a counterclockwise spiral, giving me a climb milling toolpath. If I was working from the top down, then she's going to conventional mill. So just keep that in mind. Certainly if I was on an OD scenario, then I'm probably going to want to work from the top down, ensuring that I am climb milling at that point. Right-hand thread, that would be pretty important. That is working obviously in conjunction with the Z1 to Z0 field. Internal as well. Now the number of teeth, that is how many teeth I physically have up my thread mill. So you can sit there and try to count out each little tip on the thread mill. I just used a quick scale. Whatever measurement I saw there, I divided it by my pitch, told me effectively how many teeth I have, and then I plugged it in. Now this is important because I'm going to give it a depth of my thread, and the system's going to calculate, do I have enough geometry there to cut it in one shot? If it doesn't, then it's going to take it and kind of in stairs. So it'll come down, however many teeth that you tell it I have, take one helix, then move down further, take the next. Obviously it knows it can't go to the bottom and work its way up at that point. So it's still going to machine down and up, but it's going to break this strategy up into maybe 2 or 3 passes in my Z. Effective depth of whatever I want my thread to be. Here's my pitch that we got out of the machinist's handbook. Again, this is a non-critical dimension. It's just how we calculate where the wall is, so we can lead in and lead out. And if I'm doing multiple depths of cut, then it'll use that to kind of gauge where the first cut would be. My critical dimensions right here, my 1/2 inch. And then my thread height is, I'm sorry, I got those backwards. Thread height is non-critical. Thread pitch is very, very critical because that's the helix that we're coming up. I'm always looking at the screen on a little bit of an angle when we're doing these videos, so sometimes I get lost as to which field I'm looking at. All right, so pitch, very important. That's your helix. Thread height, again, we're just using that to get our starting position and if I'm doing multiple depths of cut. So once I've filled out the page, we save the page. Now for me, quickly positioning, you could give it some rapid moves. I happen to have a cycle in the control that allows me to do a grid of holes. So I use this to program a bunch of my holes. And then for me, there's this cool little hide position feature. So in this scenario, I was just kind of dropping in a hole, taking some test cuts. So I can now turn on or off with these little check boxes which hole I want to do. So by checking just 6, it's actually going to give me this front center hole. Just a quick way for me to modify up my part program. So we're going to cut that first hole. I'm going to do a mid-program reset. I'm going to start from my thread milling operation. And I'm going to use hole 1 because there is only one hole program because I shut off all the rest. All right. And now the machine's going to go grab our OSG thread mill. I am going to come in and give us a little bit of lubricant. And now we're spiraling around. So if you look at the feed rate, and we're going to shut it off, it wasn't running the 22.5, but it was running roughly 7. We're going to run this again, but we do want to get a quick gauge on this part. So I just cut the entire geometry there in one pass. It didn't sound too bad either. Now, since I climb milled, I have a pretty good finish in the hole. I am going to just give a quick little deburr. And now, from a gauging perspective, I have a go gauge right here that we can use. Certainly, I could use the bolt, but if I start to drop in, I'm going to notice it's a bit tight. So it's just starting to engage on that geometry, right? So a couple things going on. What I have noticed with the one pass is it will be a little tighter, so you may want to add a spring pass to it. So I'm not going to change anything. I'm just going to drop right back in and take one spring pass. We'll take a look, and then we might throw a little bit more of an offset there. So let's do another program, mid-program restart. We're going to start from the thread milling again, same hole. Say OK. And now watch that feed. So there's that 7.2. So the system did the calculation. But because of that, pay attention, because obviously had I put my compensated numbers in, now I would be wrong as well. So that was just a spring pass. Again, sitting at that 1/2 inch. So I would say I want to do just a little bit more. Now what I found before when I was doing it, I actually opened up the hole about 3 thou. So let's go give that a try. So when I start sneaking up, normally you guys would be used to adjusting the tool diameter. In an application like this, I would say instead, you actually want to do it inside the threading cycle, and you want to do it right here with the major diameter. So I'm going to bump up about 3 thou, 5.003, that should be good. Now certainly when I start to gauge threads like this the first time, I'm going to want to kind of sneak up on them for sure. You see how fast that is? I mean, good luck trying to tap that hole, especially on that geometry, that size, that quickly. Not to say you couldn't do it in some materials, but I think you'd be pretty hard pressed. And there we go. So I would say that's pretty perfect. So I did have to go a little bit over. Now what's interesting, when you start to look at the dimensions that are called out right in the machinist handbook, right? If we go back to this sheet, you see how it's telling me my major diameter is 1/2 inch? Now what was interesting, when you look at the specs on the go gauge is actually 2/10 over 1/2 inch. That is the measured spec, certified spec of this go gauge. The reason being is, again, the critical dimension is not the root or the crest of this thread, it's the pitch diameter. And the pitch diameter, which is going to be right here in the center of our screen on a class 2B thread internal, is from 4675 to 4731. So that's really the dimension we want to hit. And if you look at your specs on your go gauge, that's where it's being called out from. So there's no way I could have ever gotten this tool that was already measured to be 2/10 over 1/2 inch into a hole that I machined to 1/2 inch. That's why we needed a little extra clearance there. But again, that's not the critical dimension. The OD is not. It's that pitch diameter. Okay, so if we are now at a point where we've adjusted it properly, we can certainly try to go into one last hole. Maybe we'll jump to that lower corner hole. Now, normally what I would say is you may get, I'm holding this thing pretty tight, so the 3 thou may be a little bit snug for a one-shotter, but let's try it. See if I can get away without having to deburr it. Let's try it. And there we are. So one shot. So if I was doing a lot of these holes, certainly it's going in. I might go to like 504 for any volume of production. What is amazing though, and you can see right here, this thread is as tight at the top as it is on the bottom. So I am not getting any deflection of my spindle. That left-hand helix is doing exactly what it was asked to do, which is pull that tool in and give me a very straight, and I would say really nicely cut thread. Okay, now I did mention then, what if I wanted to do a non-standard geometry? So you can use a lot of the measurements to then work from for a non-standard tool or a non-standard profile, right? So depending on what information I was given on the part print, when I had to figure out the hole size I needed to machine it to, in this case I was going to do a 1" 20. You see, I'm machining it to 9531. Well, how did I come up with that number? Well, it was easy. I took my 1/2 inch I was going to machine, and I knew I had to drill a hole of 29/64. So what's that difference? Well, that difference is going to be effectively the same difference when I do a non-standard hole. So the difference of the tap drill and my standard 1/2 inch major diameter on a 1/20, I can use that same math over here. So that's where I calculated the 4931. When I go down into the thread mill here, now really everything else is effectively the same, except I want to make sure I adjust my major diameter. Now it's 1 inch. And my height's going to stay the same, my pitch is the same, everything else is really the same, obviously around my part geometry, so maybe my depth would be different or something. I used a quick little position just to do it at the center of my part. So now let us machine that, and where I want you to pay attention is the calculated feed rate. Remember before it was machining roughly 7 inches a minute? So I got the same feeds and speeds. Actually, in fact, just to show you, in case you didn't notice it, I got the same feeds and speeds here. Now, obviously, I calculated out the new effective, actually, no, that should be, what was it, 22.5, I think it was, 22.5. And then my RPM should still be 4,500. There it is, right? And watch the feed rate, oops, that we're actually going to run this at. Now in this one, I think I did a couple depths per pass just to show you, but look at the feed. Now it's going 14 inches a minute because I'm at a much larger geometry, right? So that calculation, and actually if you watch each pass, it is going to adjust that feed slightly. They were at 14.6, now we're at 14.8. So keep that formula into the back of your head. If you're on a SINUMERIK, this is the why reason as to why my system is going faster or slower than I programmed. It's because the controller is doing the calculation for you. If you're not running a SINUMERIK, or you happen to be maybe doing it without one of the CAN cycles, then you absolutely need to do the math, do that calculation. Okay, so we've gone through. I do notice we're running a little long, and I'm going to keep going. So if you guys want to hang out, by all means. We usually go about a half an hour on these events. But we did want to do a pipe thread, right? There are a couple extra dimensions that I have to think about when I'm going to machine a pipe thread. Now first, I didn't have a go gauge for this. I wanted to come up with something so I could give myself a rough baseline of where my engagement point would be, right? In a tapered pipe thread, it's going to lock in the middle of the thread. So what I did was I just grabbed a fitting. I had a barb here and a male and female fitting. I tightened it in until I was hand tight. I blued up this red ring you might see there, and that gave me my engagement point. So I could use this when I started to machine my part. And then obviously we're going to come in and we're going to cut a few. So when you start to kind of work the numbers, right, and do some calculations, and let's jump over to our, oh, I jumped over my gauging slide. All right, well, let's talk about gauging real quick before we get into the MPT. So you did notice that I was gauging this with a go gauge. Pretty standard practice when you come through and start gauging threads. However, you know, there's a lot of trial and error slowly sneaking up because I don't really have a good number. I just know this tool either fits or it doesn't fit anymore, and then I've gone over size. So OSG does have a nice series of additional gauging tools outside of your normal go, no-go gauge. There's the diameter correction tool in the lower left-hand corner of your screen. So that's kind of a more of a manual type of scenario. But what it does is the thread on that is a little undersized, and then as I bring it in and seat it into the thread, there's a secondary portion of that gauge that will tell me how undersized or oversized I am on the thread geometry. So I get an actual numerical value to represent how much more I have to cut. On the right side, there is also a digital version of that. So certainly if you're doing a lot of the same thread profiles, the digital is just going to give me a little bit more simpler value, but it really works the same way between the two tools. So I can jump between the manual or the digital. Okay, but back to our MPT. This is the profile we're going to cut. And I do see some questions coming up. I will go back and answer them at the end. It's always tough to kind of stop and spin, switch back to some of the questions. So just hang on, we'll get to them at the end of the event. So when I get to an MPT thread, I got to work from some common values like I saw before, but there are a few things that you want to watch out for with an MPT. So certainly my pitch, that can be pulled right out of my machine's handbook. That's going to be my p-value there, and that's a 0.07143. All right, that would also be easily calculated like before, 1 divided by 14 in this case, because we're doing a half by 14. My hole size, that I don't have to go to another reference. I can pull that right out of the machinery handbook, and that's that K0 value. So that's a 0.7013 dimension. So that is going to be effectively what we want to machine that hole to. Now, if I'm using a single tooth thread mill, I would also have to pre-machine a cone before I start cutting it, because the tool never machines the outside of the profile of my thread. It's only really getting the V and the root of the thread. On these multi-tooth thread mills, they're machining both the bottom and the top of the profile for me. So I only have to do is prep a straight hole through this part of whatever this minor hole size is, and that cutter will handle cutting the entire thread mill for me, taper and all. So it really does kind of streamline my operation a little bit more effectively than using a single tooth tool. Okay, now the depth, this is where you want to watch out. I've actually seen some people on YouTube they were calling out the depth of an ID thread as the L4 dimension, which is your overall thread length of 0.7815. That is not the depth for an internal MPT thread. The actual depth is your L1 and L3 dimension added together. So if you look at L1, we have a value of 0.320. If you look at L3, we have a value of 0.2143. So that is the total dimension that I need to cut. And it equals out to just over a half an inch, 0.5343. If I was to program the 7815, that's going to way overcut my geometry, and my standard is going to then bottom right out, or in this case, my fitting. My thread height, pulled right out of the machine's handbook, 057. The major diameter, that was the value that I couldn't find anywhere, right? Now, keep in mind, everything works off the pitch diameter, so effectively the major normally would not be all that critical. However, on a CNC mill, I have to program from the major. So in my case, what I did was I took my hole size, which should be effectively my minor, of 701. I took my thread height, which I was told is my 0.0571, multiplied that by 2, added that on the 701, and that gave me my 81558, or my major diameter. After cutting it, I stayed a little undersized. I found I was about 5 thou under that. I think at the end we programmed 8 to 10. You do have a lot more forgiveness with an MPT thread. Yes, some of them bottom out a little bit further, so you have to keep that within reason. But remember, you're just engaging the center of that thread, so there's a lot more kind of freedom when it comes to that depth. Certainly, if I'm trying to do this to any real tight tolerance, get yourself a gauge to be able to measure that. Tool specs, same as we did before. So there's my RPRG value right off of my package. Now that's what's happening at the tip of the tool. That's the most critical portion of this. So that's how I came up with a tool diameter of 5723. Speeds and feeds, all same things come into play like we saw before. So let's load up. Clean up a little bit. Let's load up our MPT. All right. I did the same thing as I did before in the program, so I just have a grid of holes, allows me to just kind of isolate one at a time. I used 2 different offsets, 54 and 55. This way I wouldn't have to reset it up during the event. Now the program is going to look very similar. So here we have our MPT thread. Now some of you may be looking at my screen and wondering, gee, Chris, that looks a little different than the last event you did. So I'm proud to say that we have just converted this machine over to our latest variation of the control. So this is the SINUMERIK 1 control. It's touchscreen based, a lot larger than I had on my 828. It's got all kinds of new features and functions, so stay tuned. We're going to be showcasing a lot of new cool stuff on this channel, driven from the SINUMERIK 1 control. So a shout out to my buddy Brian Baumgartner. He's one of our engineers that did a great job converting this machine from its previous 828 to the latest SINUMERIK 1. Now, back to our program. So here I just drilled a couple prep holes. I just used the 29/64 drill because I did want to punch something through. And then, in my case, I didn't have a 701 drill, so I just did a simple pocketing cycle, bringing it to that 701 ID that I was told off of the machinery handbook. Now we jump into the thread mill. It's going to look extremely similar. You notice there's nothing here that says anything about taper because that's being driven by the tool geometry. Our multipass cycle does not allow you to do a tapered geometry with like a single point tool. You have to use a tool that has been ground in. If you wanted to do a single point tapered thread, you would have to program that longhand or do it externally. So everything else really works the same. So my calculated feeds and speeds, obviously my numbers are a little different because I have a different tool radius, I have a different diameter that I'm machining to. but those are where these values came from. Bottom to top, I want a climb mill. That's all the same, right hand internal. Number of teeth, same scenario. If I don't have enough room, then it'll take it in a couple passes, moving up or down in the Z. Certainly my overall thread depth, so that was where I used my, what was it, the L1 and the L3 dimensions added together. That's where I got my depth from. That's a critical dimension in a pipe tap, where it's not as critical, obviously, in a straight thread. Threads per inch, or put my pitch in, either one. Remember I said I did stay off of it by a little bit, so there's my 810 as opposed to 815, which the math came out to. Thread height came right out of my machinist handbook. Now in this case, I'm doing a couple passes. You can effectively cut this in one shot. My machine isn't maybe quite as rigid, so I found, not that it was struggling, but it didn't sound as good as I would want it. So in this scenario, and you think about it, there's a lot of tool pressure there with it machining the taper portion too. So I let it do it in a couple passes. And other than that, I brought everything else to size. So I have some positions here. We're going to just trigger the next hole that has not been threaded. Save that. And let's go cut it. Now what's cool about our block search, our mid-program start, is it'll recognize there's multiple operations on the same holes. It allows me to pick what operation I want to start from, and then if there's multiple holes, which hole I even want to start from. Say OK. All right. Grabbing our tapered thread mill. All right, just need to adjust my coolant line just a little bit. I'm trying to keep the amount of coolant down here. Usually I use the through spindle coolant, or the around cartridge coolant, shall I say. But in this case, with the cameras, I'm trying to reduce the volume of coolant so we don't splash. And here you see the difference in feed rate. So now we programmed, what was it, 13 or so. It's running at under 3 because of the size of the tool in relation to the radius I'm cutting, right? It's actually even a smaller circle. There's our next pass, so now it kicked up to 3.5. And then I think we got one more pass programmed in this case. So here I was getting a little bit on the engagement right there. And then when we just about pull off, little bit of chatter. I attribute that mostly to just the machine rigidity in this scenario. All right, and let's bring her out. Take a quick peek. I don't know if you guys can see, even with that little bit of noise we were seeing, boy, there is nothing visible in that finish. That is just a beautiful finish. Unfortunately, I don't think the cameras will do it justice. And here we gauge in, and you notice I'm just getting tight right around that red mark, if you guys can see that there on the side. Okay, so we have had some questions come in. Usually I have a cohort here reading the questions, but today I'm on my own, so let's take a quick look. So how do we make a 2-inch MPT thread mill program for the machine, Fanuc, Mitsubishi, and Haas? How do we make a tapered thread mill program? Any 2D program techniques or any 3D software? Okay, so from a software perspective, I mentioned it maybe even after the person got a chance to put this question in. Oops. What I would say, take a look at the OSG website. So they have a great little program tool that will give you a program specific to this tool. So you're not going to necessarily use it if you're using a non-OSG tool, but it's been designed to optimize the tool path for this specific cutter geometry. So you go in, you put your thread specs in, it's going to then even show you and make a recommendation on the tool you should use, and then it'll spit out the code. What we can also do, maybe I'll follow this up with another event where I'll program it right on the control and give you also a couple solutions of how I could do that manually. But that'll certainly work on any of those competitor controls you mentioned. All right. Oh, okay. Yeah, good call. So Andy was mentioning that you got to watch the depth, because if you looked closely at our cycle, we're actually dropping slightly below the Z1. And I think that's because it's taking into account the profile of the thread and the pitch of the thread, and it's adding that to the Z1. So as it rolls in, you're actually getting a full length of thread right to Z1. If you think about it, I can't start cutting there, or I'm going to be losing about 1 lead of the thread. So I think that's where you're seeing that extra step down. Okay. So yeah, Brian mentioned, I see Brian's on it. So this is the new PPU 1740, our new SINUMERIK 1 control. So like I said, stay tuned. We're going to have a lot of new content streaming on that for sure. So the cycle is the same. I think they're asking, is the cycle the same on the SINUMERIK 1 to the 840, 828? Yeah, it's the exact same cycle. Everything you saw will program the same way on any of the controls that we make. I believe even in the 808, although the 808 is a slightly different, older legacy cycle. With tapered thread milling, there's usually only enough teeth to cut the correct depth. That is absolutely true. So when I first cut, and I was just proving out this tool, I mistakenly used that overall dimension, and it buried that tool. There was just enough, believe it or not, to make it, but it went majorly oversized. So generally speaking, yes, on a thread mill, they're going to give you the correct length of thread for the correct geometry of the tool. Is that shop mill? Yeah, so what I programmed this in was in shop mill. The cycles look the same from the G-code side. So had I actually had created the program in G-code, right? So we'll just use G-code and give it, I don't know, just some random name. When you go into our milling cycle and you go to thread milling, this is going to be the same scenario. So everything I talked about, strategy and the numbers and how I plug it in, doesn't really matter if you program in shop mill or in G-code. Only different here, my feeds and speeds are done outside of the cycle in G-code as opposed to right in the CAN cycle with shop mill. Okay, and I think I got all of the questions. If not, you guys can always reach out to me, put a comment. Hopefully you certainly found this enjoyable. I did as well. I always enjoy doing these things. So with that, thank you for joining. Please remember, if you're not, subscribe to our channel. Make sure you like it, and by all means share it. The more you guys promote this content and engage with us, the more videos we'll be able to do. So with that being said, thank you for joining another episode of Simply SINUMERIK Live, and I look forward to seeing you next time. Have a great day.